right, welcome. Today is a nice chill day. We're gonna start learning some Rust. We're gonna go through Jon Gjenset's, I think that's how you pronounce his name. We're gonna go through his new book. If you don't know who that is, I posted all the links on him I could find in the description. But you probably do know who that is, and if you don't, you should just go to his channel right now because everything he does is better than me. So, um, we're going to go through the first chapter of his book. I sort of flipped through it, and it doesn't look like there's a ton of coding in this chapter. So if you're looking for a code-heavy stream, you might want to come back for some of the later chapters. But this is just going to be a nice chill through, surprise, surprise. It's a book. There's going to be reading involved. So let's get going. Let me see if I can, nice. All right. Obviously, if there is any code, we can, go through that. But so I'm skipping the intro because that's just some pretty basic information about what the book is about, what's it going through, who Jon is, that sort of thing. Basically, Jon's great, and the book is for anyone that has pretty much finished the introductory book to Rust, the book, which is also great. But yeah, here we go. So as you dive into more advanced corners of Rust, it's important that you ensure you have a solid understanding of the fundamentals. In Rust, as in any programming language, the precise meaning of various words and concepts becomes important as you begin to use the language in more sophisticated ways. In this chapter, we'll walk through as many of Rust primitives and try to define more clearly what they mean, how they work, and why they are exactly the way they are. Specifically, we'll look at how variables and values differ, how they are represented in memory, and the many different memory regions a program has. We'll then discuss some of the subtleties of ownership, borrowing, and lifetimes that you'll need to have a handle on before you continue with the book. Yeah, so I think most of the chapters of the book are, see if he says it here. Yeah, I think most of the chapters of the book you can read pretty independently, except for this one, because you sort of have to know all this stuff. If you already know all this stuff, you can just go to whatever chapter you want, I think. You can read this chapter from top to bottom if you wish, or you can use it as a reference to brush up on concepts that you feel less sure about. I recommend that you move on only when you feel completely comfortable with the content of this chapter, as misconceptions about how these primitives work will quickly get in the way of understanding the more advanced topics or lead you to using them incorrectly. Okay, so that's cool. So it's like what I just said nested in this chapter, where if you don't understand a given section, you can just go back to it and figure out what it is. Okay, talking about memory. Not all memory is created equal. In most programming environments, your programs have access to a stack, a heap, registers, text segments, memory mapped registers, memory mapped files, and perhaps non-volatile RAM. All right, well, this is great because I don't know what some of these things are. Which one you choose to use in a particular situation has implications for what you can store there, how long it remains accessible, and what mechanisms you use to access it. The exact details of these memory regions vary between platforms and are beyond the scope of this book. Oh, well, I guess we're not going to talk about it. But some are important to how you reason about Rust code, but they are worth covering here. Okay, so maybe it's like more lower layer stuff just has done that for you, but written in Rust still. Memory terminology. Before we dive into regions of memory, you first need to know about the difference between values, variables, and pointers. A value in Rust is the combination of a type and an element of that type's domain of values. A value can be turned into a sequence of bytes using its type's representation, but on its own you can think of a value more like what you, the programmer, meant. For example, the number 6 is the type U8, and the type U8 is an instance of the mathematical integer 6, and its in-memory representation is the byte 0x06. Similarly, the string hello world, or the str, it's different, is a value in the domain of all strings whose representation is UTF-8 encoding. Okay, a value's meaning is independent of the location where those bytes are stored. A value is stored in a place, which is the Rust terminology for a location that can hold a value. This place can be on the stack, on the heap, or in a number of other locations. The most common place to store a value is a variable, which is a named value slot on the stack. Yeah, so there's like what you see when you write the code as a place, and then there's, you know, from computer science, like the stack and the heap as a place, and then there's like physically what's on the machine as a place. So this is good. A pointer is a value that holds the address of a region of memory. So the pointer points to a place. A pointer can be dereferenced to access the values stored in the memory location it points to. Yeah, so you got like the box, and then what's in the box, and then you can tell the pointer to look in the box by dereferencing. Okay, we can store the same pointer in more than one variable, and therefore have multiple variables that indirectly reference the same location in memory, and thus the same underlying value. Consider the code in listing 1.1, which illustrates these three elements. Let x equal 42, y equal 43, var1 equal ampersand x, and then let mut var2 ampersand x. I don't think this works. I don't think you can have a mutable variable and an immutable variable. And then var2 equals reference to y, which is totally separate. So let's zoom out a bit so we can see both. Here there are four distinct values, 42 and I32, 43 and I32, the address of x, a pointer, and the address of y, a pointer. Right, so these are pointers to these numbers, which are I32s. There are also four variables, x, y, var1, var2. The latter two variables both hold values of a pointer type. So these are both pointers. Yeah, because references are pointers, right? While var1 and var2 store the same value initially, they store separate independent copies of that value, where we change the value stored in var2. The value in var1 does not change. In particular, the equals operator stores the value of the right-hand side expression in the place named by the left-hand side. Yes. An interesting example of where the distinction between variables, values, and pointers becomes important is in statements such as, so I guess that does work. I guess I was wrong. Interesting. Let string equal hello world. Even though we assign a string value to the variable called string, the actual value of the variable is a pointer to the first character in the string value hello world, and not the string value itself. At this point, you might say, but hang on, where's the string value stored then? Where does the pointer point? So you have a keen eye, and that we'll get to in a second. Yeah, so you're saying like, this doesn't hold this. It holds a pointer to this and information. I think that's what it's saying. The value of string also includes the string length. Yeah, so that's the information. We'll talk about that in chapter 2 when we discuss wide pointer types. Okay, cool. Variables in depth. The definition of a variable I gave earlier is broad and unlikely to be all that useful in and of itself. As you encounter more complex code, you'll need a more accurate mental model to help you reason through what the program's really doing. There are many such models that we can make use of. Describing them all in detail would take up several chapters. It's beyond the scope of this book. But broadly speaking, they can be divided into two categories: high-level models and low-level models. High-level models are useful when thinking about code at the level of lifetimes and borrows, while low-level models are good for when you are reasoning about unsafe code and raw pointers. Okay, interesting. The models for variables described in the following two sections will suffice for most of the material in this book. Okay. So let's see what he's saying here. High-level model. In the high-level model, we don't think of variables as places that hold bytes. Instead, we think of them just as names given to values as they are instantiated and moved and used throughout a program. When you assign a value to a variable, that value is from then on named by that variable. When a variable is later accessed, you can imagine drawing a line from the previous access of that variable to the new access, which establishes a dependency relationship between the two accesses. If the value in a variable is moved, no lines can be drawn from anymore. Okay. In this model, a variable exists only so long as it holds a legal value. You cannot draw lines from a variable whose value is uninitiated or has been moved. So effectively, it isn't there. Using this model, your entire program consists of many of these dependency lines, often called flows, each one tracing the lifetime of a particular instance of value. Flows can fork and merge when there are branches with each split. So flows can fork and merge when there are branches. Each can split tracing at distinct lifetime. With each split tracing a distinct lifetime for that value. The compiler can check that at any given point in your program. All flows that can exist in parallel with each other are compatible. For example, there cannot be two parallel flows with mutable access to a value. Nor can there be a flow that borrows a value while there is no flow that owns that value. So the value has to be owned and cannot be owned multiple times. I think that's what that says. Let's see the example of both these cases. Okay. Let mut x, this access would be illegal, nowhere to draw the flow from. Cert x is 42. This is okay. Can draw a flow from the value assigned above. So you can't do this. You can draw a flow from the value assigned above. This establishes a second mutable flow from x. I think you can't do this. So x equals 43. This continues the flow from y, which in turn draws from x. But that flow conflicts with the assignment to x. So you're setting in a mutable x, and then you're setting x equal to 42, and then you're setting y to a pointer to x. No. This is the value of x. And then you're setting x to 43. But then there's a conflict. That makes sense. Okay. So First, we cannot use x before it is initialized because we have nowhere to draw the flow from. Only when we assign a value to x can we draw flows from it. This code has two flows, one exclusive, &mute, flow from 1 to 3, going from here to here, and one shared, ampersand, flow from 1 to 2. 1 through 2 to 4. Dereferencing y. Okay, this is starting to make more sense. The borrow checker inspects every vertex of every flow and checks that no other incompatible flows exist concurrently. In this case, when the borrow checker inspects the exclusive flow at 3, it sees the shared flow that terminates at 4. Since you cannot have an exclusive and a shared use of a value at the same time, the borrow checker correctly rejects the code. Notice that if 4 was not there, this code would compile fine. The shared flow would terminate at 2. And when the exclusive flow is checked at 3, no conflicting flows would exist. Right. Okay. If a new variable is declared with the same name as the previous one, they are still considered distinct variables. This is called shadowing. The later variable shadows the former by the same name. The two variables coexist. The subsequent code no longer has a way to name the earlier one. This model matches roughly how the compiler, and the borrow checker in particular, reasons about your program, and is actually used internally in the compiler to produce efficient code. Huh. That's pretty neat. Low-level model. Variables name memory locations that may or may not hold legal values. You can think of a variable as a value slot. When you assign to it, this slot is filled, and its old value, if it had one, is dropped and replaced. When you access it, the compiler checks that the slot isn't empty, as that would mean the variable is uninitialized or its value has been removed. Pointer to a variable refers to the variable's backing memory and can be dereferenced to get at its value. For example, in the statement let x usize, the variable x is a name for a region of memory on the stack that has room for a value the size of a usize. Though it does not have a well-defined value, its slot is empty. If you assign a value to that variable, such as with x equals 6, that region of memory will then hold the bits representing the value of 6. $x does not change when you assign to x. If you declare multiple variables with the same name, they still end up with different chunks of memory backing them. This model matches the memory model used by C and C++ and many other low-level languages, and is useful when you need to reason explicitly about memory. In this example, we ignore CPU registers and treat them as an optimization. In reality, the compiler may use a register to back a variable instead of a region of memory if no memory address is needed for that variable. Okay. Sort of helping us peek behind the curtain of what he's teaching us, which is nice. You may find that one of these matches your previous model better than the other, but I urge you to try to wrap your head around both of them. They're both equally valid, and both are simplifications. Yeah, like any useful mental model has to be. If you're able to consider a piece of code from both of these perspectives, you will find it much easier to work through complicated code segments and understand why they do or do not compile and work as you expect. Okay. Some of that wisdom from experience is dropping on us. Memory regions. Now that you have a grip on how we refer to memory, we need to talk about what memory actually is. There are many different regions of memory, and perhaps surprisingly, not all of them are stored in the DRAM of your computer. Which part of your memory you use has a significant impact on how you write your code. The three most important regions for the purposes of writing Rust code are the stack, the heap, and static memory. Okay. The stack. The stack is a segment of memory that your program uses as scratch base for function calls. Each time a function is called, a contiguous chunk of memory called a frame is allocated at the top of the stack. Near the bottom of the stack is the frame for the main function. And as functions call other functions, additional frames are pushed onto the stack. A function's frame contains all the variables within that function, along with any arguments the function takes. When the function returns, its stack frame is reclaimed. The bytes that make up the value of the function's local variables are not immediately wiped, but it's not safe to access them as they may have been overwritten by a subsequent function call whose frame overlaps with the reclaimed one. Okay. And even if they haven't been overwritten, they may contain values that are illegal to use, such as ones that were removed when the function returned. Okay. Stack frames and crucially, the fact that they eventually disappear are very closely tied to the notions of lifetimes in Rust. Any variable stored in a frame on the stack cannot be accessed after that frame goes away, so any reference to it must have a lifetime that is at most as long as the lifetime of the frame. That starts to make more sense. Because like you mess up a bunch with lifetimes like in code blocks, but if you think of it as the stack and then the frames in the stack, and then within a frame you have to be consistent. That makes sense. The heap. The heap is a pool of memory that isn't tied to the current call stack of the program. Values in heap memory live until they are explicitly deallocated. This is useful when you want a value to live beyond the lifetime of the current function's frame. If that value is the function's return value, the calling function can leave some space on the stack for the calling function to write that value into before it returns. But if you want to, say, send that value to a different thread, with which the current thread may share no stack frames at all, you can store it on the heap. It's interesting. I had not thought of the heap with regards to threads, which seems like a pretty short leap, but I never did it, so oh well. The heap allows you to explicitly allocate contiguous segments of memory. When you do so, you get a pointer to the start of that segment of memory. That memory segment is reserved for you until you later deallocate it. This process is often referred to as freeing, after the name of corresponding function in the C standard library. Since allocations from the heap do not go away when a function returns, you can allocate memory for a value in one place, pass the pointer to it to another thread, and have that thread safely continue to operate on that value. Or phrased differently, when you heap allocate memory, the resulting pointer has an unconstrained lifetime. Its lifetime is however long your program keeps it alive. Yeah, when I first got introduced to computer science, it was in like an intro to C class, and all of these memory errors almost ruined it for me, so thank goodness for Rust. The primary mechanism for interacting with the heap in Rust is the box type. When you write box new value, the value is placed on the heap, and what you are given back, the box t, is a pointer to that value on the heap. When the box is eventually dropped, that memory is freed. Just this one paragraph is like so helpful, because when you start doing Rust, you just like put everything in a box and just have no idea why it works, and it's just black magic. But it's pretty straightforward. You can say it in a couple sentences. It's nice. If you forget to deallocate heap memory, it will stick around forever, and your application will eventually eat up all the memory on your machine. This is called leaking memory, and is usually something you want to avoid. However, there are some cases where you explicitly want to leak memory. For example, say you have a read-only configuration that the entire program should be able to access. You can allocate that on the heap and explicitly leak it with box leak to get a static reference to it. Interesting story about leaked memory. I used to play Magic the Gathering, and on the online version, their program just had like a built-in memory leak, and it was so bad, and they never fixed it. And they never fixed it to the point where the new version literally has like the help tips, and it says like experienced players know to restart their program after every match. It's ridiculous. So again, thank goodness for Rust. Static memory. Static memory is really a catch-all term for several closely related regions located in the file your program is compiled to. Okay. These regions are automatically loaded into your program's memory when that program is executed. Values in static memory live for the entire execution of your program. Your program's static memory contains the program's binary code, which is usually mapped as read-only. See, I didn't know any of this. This is great. As your program executes, it walks through the binary code in the text segment instruction by instruction by instruction and jumps around whenever a function is called. Static memory also holds the memory for variables you declare with the static keyword. Ah, see, I didn't know that, which I've used, but didn't know. As well as certain constant values in your code, like strings. That's one of the great things about Rust is like the compiler tells you what to do, so even if you don't know what you're doing, you can sort of figure out how to do it. But after you've done something, you can then go and read stuff like this, where like, now I understand, I know what a box is, I know what static is. It's like, it seems like a much better way to learn than the other way, than the reverse. The special lifetime static, or tick static, which gets its name from the static memory region, marks a reference as being valid for as long as static memory is around, which is until the program shuts down. Since a static variable's memory is allocated when the program starts, a reference to a variable in static memory is, by definition, tick static, as it is not deallocated until the program shuts down. The inverse is not true. There can be tick static references that do not point to static memory, but the name is still appropriate. Once you create a reference with a static lifetime, whatever it points to might as well be in static memory as far as the rest of the program is concerned, as it can be used for however long your program wishes. You encounter the tick static lifetime much more often than you encounter truly static memory, through the static keyword, for example, when working with Rust. This is because tick static often shows up in the trait bounds on type parameters. A bound like t_tick_static indicates that the type parameter t is able to live for however long we keep it around for, up to and including the remaining execution of the program. Essentially, this bound requires that t is owned and self-sufficient, either in that it does not borrow other non-static values, or that anything it does borrow is also tick static, and thus will stick around until the end of the program. A good example of tick static as a bound is the standard thread spawn function that creates a new thread. which requires that the closure you pass it is tick static. Since the new thread may outlive the current thread, the new thread cannot reference to anything stored on the old thread stack. That makes sense? The new thread can refer only to values that will live for its entire lifetime, which may be for the remaining of the duration of the program. I guess that's why you have to do like move and clones before you do closures sometimes. So that's interesting. You may wonder how const differs from static. I do wonder that. The const keyword declares the following item as constant. Constant items can be completely computed at compile time, and any code that refers to them is replaced with the constant's computed value during compilation. A constant has no memory or other storage associated with it. It's not a place. You can think of constant as a convenient name for a particular value. Okay, that's cool. Rust's memory model centers on the idea that all values have a single owner. That is exactly one location, usually a scope, is responsible for ultimately deallocating each value. This is enforced through the borrow checker. If the value is moved, such as by assigning it to a new variable, pushing it to a vector, or placing it on the heap, the ownership of the value moves from the old location to the new one. At that point, you can no longer access the value through variables that flow from the original owner, even though the bits that make up the value are technically still there. Instead, you must access the moved value through variables that refer to its new location. Some types are rebels and do not follow this rule. If a value's type implementation implements the special copy trait, the value is not considered to have moved even if it is reassigned to a new memory location. Instead, the value is copied, and both the old and new locations remain accessible. I always wondered why people said, like, you should only copy if you have to, which makes sense. But, like, it causes bloat and whatnot. Essentially, another identical instance of that same value is constructed at the designation of the move. Most primitive types in Rust, such as the integer and floating point types, are copy. To be copy, it must be possible to duplicate the type's values simply by copying other bits. This eliminates all types that contain non-copy types, as well as any type that owns a resource it must deallocate when the value is dropped. To see why, consider what would happen if a type like box were copy. If we execute box2 equals box1, and box1 and 2 would both believe that they own the heap memory allocated for the box, and they would both attempt to free it when they went out of scope. Freeing the memory twice could have catastrophic consequences. When a value's owner no longer has use for it, it is the owner's responsibility to do any necessary cleanup for that value by dropping it. In Rust, dropping happens automatically when the variable that holds the value is no longer in scope. Types usually recursively drop values they contain. So dropping a variable of a complex type may result in many values being dropped. Because of Rust's discrete ownership requirement, we cannot accidentally drop the same value multiple times. A variable that holds a reference to another value does not own that other value, so the value isn't dropped when the variable drops. Okay. The listing in 1.3 gives a quick summary of the rules around ownership, move, and copy semantics, and dropping. Move and copy semantics. Okay. So x1 is 42, y1 is box new 84, and then we start a new scope. So z is the tuple of x1, y1, and then z goes out of scope and is dropped. It in turn drops the values from x1, y1. So z has ownership here of these two. but then ownership is moved back to these two here once Z gets dropped. X1's value is copy, so it was not moved into Z. Right, this was a reference. Let x2 equal x1. Y1's value is not copy, so it was moved into Z. So you can't say y2 equals y1. Okay, so he's saying this is copy because it's on the stack. I think it's on the stack. So here, this is a reference. But this is on the heap because it's a box, which means that this is not a reference. This is a copy of the heap allocated memory. So when Z gets dropped, Y gets dropped, but X1 does not. Gotcha. We start out with two values, the number 42 in a box, a heap allocated value, containing the number 84. The former is copy, whereas the latter is not. Let's see if I'm right. When we place x1 and y1 into the tuple Z, x1 is copied into Z, whereas y1 is moved into Z. Oh, I said it backwards. I meant this, but I said it backwards, I think. At this point, x1 continues to be accessible and can be used again. On the other hand, y1 is rendered inaccessible once its value has been moved, and any attempt to access it would incur a compiler error when Z goes out of scope. The tuple value it contains is dropped. And this in turn drops the value copied from x1 and the one moved from y1. When the box from y1 is dropped, it also deallocates the heap memory used to store y1's value. Gotcha. Okay, so we got a special box here for drop order. Rust automatically drops values when they go out of scope, such as x1 and y1 in the inner scope of listing 1.3. The rules for the order in which the drop are fairly simple. Variables, including function arguments, are dropped in reverse order, and nested values are dropped in source code order. This might seem weird at first. Why the discrepancy? If we look at it closely, though, it makes a lot of sense. Say you write a function that declares a string and then inserts a reference to that string into a new hash table. When the function returns, the hash table must be dropped first. If the string were dropped first, the hash table would then hold an invalid reference. In general, latter variables may contain references to earlier variables. Okay, yeah, this makes sense. You like can't have it empty, so you have to eat up the chain from the bottom. I don't know, that makes sense in my head. I don't know if that makes sense out loud. If the string were dropped first, the hash table would then hold an invalid reference. In general, later variables may contain references to earlier values, whereas the inverse cannot happen due to Rust's lifetime rules. And for that reason, Rust drops variables in reverse order. Now, we could have the same behavior for nested values, like the value in a tuple, array, or struct, but that would likely surprise users. Okay, if you constructed an array that contained two values, it'd seem odd if the last element of the array were dropped first. The same applies to tuples and structs, where the most intuitive behavior is for the first tuple element or field to be dropped first, and the second, and so on. Unlike for variables, there is no need to reverse the drop order in this case, since Rust doesn't currently allow self-references in a single value. So, Rust goes with the intuitive option. Okay. Okay, so here we're going to hit on the two big ones with Rust of borrowing and lifetimes. This is where a lot of new people, including myself, get tripped up. So Rust allows the owner of a value to lend out that value to others without giving up ownership through references. References are pointers that come with an additional contract for how they can be used, such as whether the reference provides exclusive access to the referenced value, or whether the referenced value may also have other references point to it. Shared references. A shared reference, $t, is, as the name implies, a pointer that may be shared. Any number of other references may exist to the same value, and each shared reference is copy. So you can trivially make more of them. So you're copying the reference, not the value. Values behind shared references are not mutable. You cannot modify or reassign the value a shared reference points to, nor can you cast a shared reference to a mutable one. And that makes sense, right? Because you don't want to, like if A points to a number and B points to a number, you want B to always know what the number is, even if A changes it. So you just make it so A can't change it. So let's see. The Rust compiler is allowed to assume that the value a shared reference points to will not change while that reference lives. For example, if the Rust compiler sees that the value behind a shared reference is read multiple times in a function, it is within its rights to read it only once and reuse that value. More concretely, the assertion in listing 1.4 should never fail. So we got a cache function of an input and a sum with a non-mutable I32 reference and a mutable I32 reference. So the dereference sum is mutable, so you can say it's input plus input. But that sum should always be twice the value of the input, because the value of the input shouldn't change. Right. Whether or not the compiler chooses to apply a given optimization is more or less irrelevant. The compiler heuristics change over time, so you generally want to code against what the compiler is allowed to do rather than what it actually does in a particular case at a particular moment in time. So, mutable references. The alternative to a shared reference is a mutable reference. Ampersand mut t. With mutable references, the Rust compiler is again allowed to make full use of the contract that the reference comes with. The compiler assumes that there are no other threads accessing the target value, whether through a shared reference or a mutable one. In other words, it assumes that the mutable reference is exclusive. This enables some interesting optimizations that are not readily available in other languages. Take, for example, the code in this. Yeah, so like in the AV example, another solution is to just say you can't have a B, right? You can only have a mutable A, or mutable reference of A. So we have a no alias function with a input that is not mutable and an output that is mutable. So if the input is 1, the output is 2. You set the output to 2. If the input is not 1, set the output to 3. Yeah, so this input isn't going to change. The output could. Assumes that mutable references are exclusive. In Rust, the compiler can assume that input and output do not point to the same memory. Therefore, the reassignment of output at 1 cannot affect the check at 2. And the entire function can be compiled as a single if-else block. Oh, that's interesting, because these are separate. So the compiler will put them together because it knows that input is not going to change, but output could. That's cool. The entire function can be compiled as an if-else block if the compiler could not rely on the exclusive mutability contract. that optimization would be invalid since an input of 1 could then result in an output of 3. In the case like no alias XX. Yeah. Because this value could change. A mutable reference lets you mutate. Well, yeah, so this value could change because it could be changed by something else. I think that's what it means. A mutable reference lets you mutate only the memory location that the reference points to. Whether you can mutate values that lie beyond the immediate reference depends on the methods provided by the type that lies between. This may be easier to understand with an example, so consider this. Mutability applies only to the immediately referenced memory. So this is immutable, this is mutable. Why is the type reference to immutable? So you can change this y, but the y is a reference. So z is a reference to the mutable y. Yeah, so z is a reference mutable of a reference I32. Only the memory location that the reference points to. Yeah. Okay, that makes sense. In this example, you are able to change the value of the pointer y to a different value, that is a different pointer. Yeah, exactly. By making it reference a different variable. But you cannot change the value that is pointed to. That is the value of x. Yeah, so x is immutable, but the pointer y is mutable, so you can change the pointer. Similarly, you can change the pointer value of y through z, but you cannot change z itself to hold a different reference. Yeah. Yeah, so you can use z to change y, but you can't change z afterwards. Because y is mutable. Y is the only thing that can change here. Okay. The primary difference between owning a value and having a mutable reference to it is that the owner is responsible for dropping the value when it is no longer necessary. Apart from that, you can do anything through a mutable reference that you can if you own the value. One caveat: if you move the value behind the mutable reference, then you must leave another value in its place. If you do not, the owner would think it needed to drop the value, but there would be no value for it to drop. Okay, yeah, so you can't like take it out, put it over here, and then put nothing there. You have to like do a quick swap or something. So this is an example of the ways in which you can move the value behind a mutable reference. So replace with 84. S is a reference to mutable heap allocated I32. This is not okay, as dereferencing S would be empty. Let was equal reference S. Oh no, this is not okay. What? But this is okay. Standard memory take. Stand mem take. So is this. The dereferenced S equals was equals this. So you take from S, you assign to was, and then you can say dereferenced S equal to was, which was taken from S. But you can't say was equals the value inside S. You can exchange values behind a mutable pointer. So let mut r equal box new 84. stand mem swap s. Okay, so instead of take, we're doing swap with a reference to mutable r. So these have to be the same type to swap them, I guess. That would make sense. And is this like nearly equals? I don't know what this is. So dereferencing r is 84 because that's the value in the box. Nice. And then that's the end of that scope. So let mut s equal box new 42, replace with 84. Then he's just got this assert in the function, which makes sense. Reference mut s. Yeah, so replacing the value of s. Access through a mutable reference must leave a value behind. Okay, let's go here. I've added commented out lines that represent illogical operations. You cannot simply move the value out in 1, since the caller would think they owned that value and would free it again at 5. Yeah, so when you run the function, it would hit this and then think that it would try to free something that doesn't exist. Yeah, leading to a double free. If you just want to leave some valid value behind, stand mem take at 2 is a good candidate. It is equivalent to stand mem replace, reference mutable value, default. It moves the value out from behind the mutable reference, but leaves a new default value for the type in its place. Right. The default is a separate owned value, so it is safe for the caller to drop when the scope ends at 5. Man, this is pretty cool. I'm learning a lot. I hope you are too. Yeah. Alternatively, I don't know why I scrolled. Alternatively, if you don't need the old value behind the reference, you can override it with a value that you already own at 3. Leaving it to the caller to drop the value later. When you do this, the value that used to be behind the mutable reference is dropped immediately. Finally, if you have 2 mutable references, you can swap their values without owning either of them. Here. Since both references will end up with a legal owned value for their owners to free. Right. To eventually free. Okay. Interior mutability. Some types provide interior mutability, meaning they allow you to mutate a value. They allow you to mutate a value through a shared reference. These types usually rely on additional mechanisms, like atomic CPU instructions, or invariance to provide safe mutability without relying on the semantics of exclusive references. These normally fall into 2 categories: those that let you get a mutual reference through a shared reference, and those that let you replace a value given only a shared reference. The first category consists of types like mutex and refcell, which contain safety mechanisms to ensure that for any value, they give a mutable reference to only one mutable reference, and no shared references can exist at a time. Under the hood, these types, and those like them, all rely on a type called unsafe cell, whose name should immediately make you hesitate to use it. Yes. We will cover unsafe cell in more detail in chapter 9, but for now, you should know that it is the only correct way to mutate through a shared reference. Okay. Other categories of types that provide interior mutability are those that do not give out a mutable reference to the inner value, but instead just to give you methods for manipulating the value in place. The atomic integer types in stand sync atomic and stand cell type fall into this category. You cannot get a reference directly to the use size or I32 behind such a type, but you can read and replace its value at a given point in time. Okay. Note, the cell type in the standard library is an interesting example of a safe interior mutability through invariance. It is not shareable across threads and never gives out a reference to the value contained in the cell. Instead, the methods all either replace the value entirely or return a copy of the contained value. Since no references can exist to the inner value, it is always okay to move it. And since cell isn't shareable across threads, the inner value will never be concurrently mutated, even though mutation happens through a shared reference. Whoa. I understood very little of that. Anyways, lifetimes. If you're reading this book, you're probably already familiar with the concept of lifetimes, likely through repeated notices from the compiler about lifetimes rules violations. Yes. That level of understanding will serve you well for the majority of Rust code you will write. But as we dive deeper into the more complex parts of Rust, you will need a more rigorous mental model to work with. That's what this book's all about. Let's do it. Newer Rust developers are often taught to think of lifetimes as corresponding to scopes. A lifetime begins when you take a reference to some variable and ends when that variable is moved or goes out of scope. That's often correct and usually useful, but the reality is a little more complex. A lifetime is really a name for a region of code that some reference must be valid for. While a lifetime will frequently coincide with a scope, it does not have to, as we will see later in the section. Lifetimes and the borrow checker. At the heart of Rust lifetimes is the borrow checker. Whenever a reference with some lifetime tick A is used, the borrow checker checks that tick A is still alive. It does this by tracing the path back to where tick A starts, where the reference was taken, from the point of use, and checking that there are no conflicting uses along that path. This ensures that the reference still points to a value that it is safe to access. This is similar to the high-level data flow mental model we discussed earlier in the chapter. The compiler checks that the flow of the reference we are accessing does not conflict with any other parallel flows. Listing 1.8, lifetimes do not need to be contiguous. Shows a simple code example with lifetime annotations for reference to x. So we have a mutable x to a heap allocated 42. So this is tick A. So R is a reference to x. So if rand is greater than 0.5, we dereference x equal to 84. Else we print R, which is tick A. Okay, let's see what he says about this. The lifetime starts at 1 here. When we take a reference to x, in the first branch 2, we then immediately try to modify x by changing its values to 84, which requires a reference to a mutable, which we have. The borrow checker takes out a mutable reference to x and immediately checks its use. It finds no conflicting uses between when the reference was taken and when it was used, so it accepts the code. This may come as a surprise if you are used to thinking about lifetimes as scopes, since R is still in scope at 2. Right. It goes out of scope at 4. But the borrow checker is smart enough to realize that R is never used later if this branch is taken. And therefore, it is fine for X to be mutably accessed here. So it's saying that at the very end of the lifetime, it can be mutated. Or phrased differently, the lifetime created at 1 does not extend into this branch. There's no flow from R beyond 2. Right. And therefore, there are no conflicting flows. The bar checker then finds the use of R in the print statement at 3. It walks the path back to 1 and finds no conflicting uses. 2 is not on that path because it's an else statement. So it would walk back, skip this, go directly to this, and say there's no conflict. And likewise, this never hits this, so there's no conflict. This would get very complicated if it was not just a toy example. So the bar checker then finds the use of R in the print statement at 3. It walks the fast back, finds no conflicting uses. Accepts this use as well. If we were to add another use of R at 4, in listing 1.8, the code would no longer compile because we've exhausted, right? If, else, that's pretty exhaustive. If it's this, if it's anything else, that's everything. If we were to add another one, code would no longer compile. The lifetime of tick A would then last from 1 all the way until 4, the last use of R, and when the bar checker checked our new use of R, it would discover conflict use at 2, right? So we try to use it again, it's already been reallocated, can't do that. Lifetimes can get quite convoluted, yes. In listing 1.9, you can see an example of a lifetime that has holes, where it's intermittently invalid between where it starts and where it ultimately ends. Let's look at these. Look at these holes. So we've got our classic mutable heap, mutable reference. So for I in 0 to 100, print Z. So it's going to print 42 100 times. It's going to try. X equals box new I. So that's separate. And then Z equals, okay, no, it's going to set it equal to the reference here, which is a new heap allocated memory. Let's see what he says. The lifetime starts at 1 when we take a reference to X. We then move out of X at 3. Right. Which ends the lifetime tick A because it's no longer valid. The bar checker accepts this move by considering tick A ended at 2, which leaves no conflicting flows from X at 3. Then we restart the lifetime by updating the reference in Z. Regardless of whether the code now loops back around to 2 or continues to the final print statement, both of those uses now have a valid value to flow from, and there are no conflicting flows, so the bar checker accepts the code. Again, this aligns perfectly with the data flow model of memory we discussed earlier. When X is moved, Z stops existing. When we reassign Z later, we are creating an entirely new variable that exists only from that point forward. It just so happens that the new variable is also named Z. With that model in mind, this example is not weird. Okay, yeah, because it's a new thing. Like it gets dropped here, I think, from being owned, and then is recreated here. And then this is immutable, but with the same lifetime. I think that's what's happening. The borrow checker is and has to be conservative. If it's unsure whether a borrow is valid, it rejects it, as the consequences of allowing an invalid borrower could be disastrous. The borrow checker keeps getting smarter, but there are times when it needs help to understand why a borrow is legal. This is part of why we have unsafe Rust. Yeah, because it has to be so strict. You need to be able to build your own loopholes in, but those loopholes need to work. Generic lifetimes. Occasionally, you need to store references within your own types. Those references need to have a lifetime so that the borrow checker can check their validity when they are used in various methods on that type. This is especially true if you want a method on your type to reference, or to return a reference that outlives the reference to self. Okay. Rust lets you make a type definition generic over one or more lifetimes, just as it allows you to make it generic over types. Rust programming language by Steve Klopnik and Carol Nichols, which I have right there, covers this topic in some detail, so I won't reiterate the basics here. But as you write more complex types of this nature, there are two subtleties around the interaction between such types and lifetimes that you should be aware of. First, if your type also implements drop, then dropping your type counts as a use of any lifetime or type your type is generic over. Essentially, when an instance of your type is dropped, the borrow checker will check that it's still legal to use any of your type's generic lifetimes before dropping it. This is necessary in case your drop code does use any of those references. If your type does not implement drop, dropping the type does not count as a use, and users are free to ignore any reference stored in your type as long as they do not use it anymore. Like we saw in listing 1.7, we'll talk more about these rules around dropping in chapter 9. Second, while a type can be generic over multiple lifetimes, making it so often only serves to unnecessarily complicate your type signature. Right. Usually, a type being generic over a single lifetime is fine, and the compiler will use the shorter of the lifetimes for any references inserted into your type as that one lifetime. You should only really use multiple generic lifetime parameters if you have a type that contains multiple references. And its methods return references that should be tied to the lifetime of only one of those references. Okay. Consider the type in listing 110, which gives you an iterator over parts of a string separated by a particular other string. Struct stir split. Yeah, he does a crust of Rust or something like this for stir split on his YouTube, so check that out. It's pretty cool. One of the few examples of multiple lifetimes. So we have a stir split struct of tick s to tick p, delimiter reference tick p stir, document reference tick s stir. So we have a delimiter and a target basically. So implementation of iterator for stir split, where item is a reference to tick s stir. So next returns an option of self item, and then this blank. So this is a type needs to be generic over multiple lifetimes. And then we have a stir before, the reference to stir and char. I don't know how you pronounce that. Returns an option, the reference to stir. So this is going to have stir split document s delimiter next. Yeah, I don't really understand this example. Let's see. When you construct this type, you have to give the delimiter and document search, both of which are references to string values. When you ask for the next string, you get a reference into the document. Consider what would happen if you used a single lifetime in this type. The values yielded by the iterator would be tied to the lifetime of the document and the delimiter. This would make stir before impossible to write. The return type would have a lifetime associated with a variable local to the function. The string produced by toString, and the bar checker would reject the code. Okay, so it's saying that you have to have a lifetime for the delimiter, which is going to basically be over the whole function, and then a lifetime that sort of chomps away at the string of the document. I think that's what he's saying. And those have to be different, or else you can't do that. Lifetime variance. Variance is a concept that programmers are often exposed to but rarely know the name of because it's invisible. At a glance, variance describes what types are subtypes of other types. Variance describes what types are subtypes of other types. Some things you just have to say fast. And when a subtype can be used in a place of a supertype, and vice versa. Variance describes what types are subtypes of other types, and when a subtype can be used in place of a supertype. Broadly speaking, a type A is a subtype of another type B if A is at least as useful as B. Variance is the reason why in Java you can pass a turtle to a function that accepts an animal if turtle is a subtype of animal. So I think when he says at least as useful, he means like a turtle is an animal, but an animal doesn't have to be a turtle. So turtle is at least an animal, but I think of it the other way. So that's like I would just say animal because that includes turtle, but I think he means the opposite way, which makes sense. Or why in Rust you can pass a reference to a tick static stir to a function that accepts a reference to a tick a stir because A is a subset of static. So this is a subtype of static. So there's variance in the lifetime, but it's nested properly, basically. While variance usually hides out of sight, it comes up often enough that we need to have a working knowledge of it. Turtle is a subtype of animal. Because a turtle is more useful than some unspecified animal. Yeah, see, I think of it in, he thinks of it in specifics, I think of it in generics. That's the issue. A turtle can do anything an animal can do, and likely more. Similarly, a tick static is a subtype of tick A because a tick static lives at least as long as any tick A and so is more useful. Right. Or, more generally, if tick B is tick A, or tick B outlives tick A, then tick B is a subtype of tick A. This is obviously not the formal definition, but it gets close enough to be of practical use. All types have a variance, which defines what other similar types can be used in that type's place. There are three kinds of variance: covariant, invariant, contravariant, like the video game. I didn't really play that game much, but nice mnemonic. A type is covariant if you can just use a subtype in place of the type, so you can like use them together. Gotcha. For example, If a variable is of type reference tick A, t, you can provide a value of type reference tick static t to it, because reference tick A, t is covariant with tick A in tick A. Reference tick A, t is also covariant in t. So you can pass a reference vector of reference tick static stir to a function that takes reference vector reference tick A stir. Gotcha. Some types are invariant, which means that you must provide exactly the given type. Okay, so invariant is like intolerant, right? It's more strict. Reference mute t is an example of this. If a function takes a reference mute vector reference tick A stir, you cannot pass it a, okay, so it's the mutability here that matters, I think. That is, a mutable reference is invariant in t. If you could, the function could put a short-lived string inside the vec, which the caller would then continue using, thinking that it were a vector of static string. Thus, the contained string were a reference to static. Any type that provides immutability is generally invariant for the same reason. For example, cell of t is invariant in t. Okay. The last category, contravariance, comes up for function arguments. Function types are more useful if they're okay with the arguments being less useful. What? This is clear if you contrast the variance of the argument types on their own with their variance when used as function arguments. So, more useful lives longer, less useful lives shorter. Right. Take function 1 and function 2. This one is stricter, so less useful. This one is less strict, so more useful. Right. Yeah, because this is saying you can't have something less than this. So that's more strict. So the function requires that it be at least this long. The variable says that it can be this long. Okay, this flipped relationship indicates that f and t is contravariant in t. So why do you need to learn about variance when it comes to lifetimes? Variance becomes relevant when you consider how generic lifetime parameters interact with a borrow checker. Consider a type like the one shown, which uses multiple lifetimes in a single field. So we have a mutable string, and then we have a reference to a tick A. So we have a mutable reference tick A. No, we have a reference of tick A to a mutable reference tick B stir. I might have said that wrong. So we've got mutable S equal hello. And then dereference mutable string takes S dot S equals world. Print line. What? What has happened? A type that needs to be generic over multiple lifetimes. At first glance, using 2 lifetimes here seems unnecessary. Yes, it does. We have no method that needs to differentiate between a borrow of different parts of the structure, as we did with stir split. But if you replace the 2 lifetimes with a single tick A, the code no longer compiles. It's all because of variance. Okay, so let's see. Note, the syntax at 1 may seem alien. It's equivalent to defining a variable x holding a mute string, mute stir, then writing dereference x dot s equals world. So we're trying to change this hello to world, except that there's no variable, and so the mute stir is dropped immediately. So at 1, the compiler must determine what lifetime the lifetime parameters should be set to. If there are 2 lifetimes, tick A is set to the to be determined lifetime of the borrow of S here. And tick B is set to tick static, since that's the lifetime of the provided string hello. So this is a tick static. So this would be tick A, and this would be tick static. But if there's just one lifetime tick A, the compiler infers that the lifetime must be tick static. When we later attempt to access the string reference S through a shared reference to print it, the compiler tries to shorten the mutable borrow of S used by mut_stir to allow the shared borrow of S. What? The mutable borrow of S to allow a shared borrow of S. And you can't have a mutable and a shared. I definitely don't understand this. But I think I sort of understand it. So let's see. When we later attempt to access the strings reference S through a shared reference to print it, the compiler tries to shorten the mutable borrow of S used by mut_stir to allow this shared borrow of S. In the 2 lifetime case, tick A simply ends just before the print line, and tick B stays the same. In the single lifetime case, on the other hand, we run into issues. The compiler wants to shorten the borrow of S, but to do so, we would also have to shorten the borrow of stir. Reference to tick static stir can in general be shortened to any reference to tick A stir because it is covariant with tick A. Here, it's behind a reference to a mutable T, which is invariant with T. Because it's mutable, it has to be exact. Invariance requires that the relevant type is never replaced with a sub or supertype. So the compiler's attempt to shorten the borrow fails, and it reports that the list is still mutably borrowed. Ouch. It's like a comic book. Ouch. Because of the reduced flexibility imposed by invariance, you want to ensure that your types remain covariant or contravariant, where appropriate, over as many of the generic parameters as possible. If that requires introducing additional lifetime arguments, you need to carefully weigh the cognitive cost of adding another parameter against the ergonomic cost of invariance. Like that, comparing cognitive costs, which is one of the great things Rust does. Just not having to track all that memory. Well, I mean, you do have to track the memory, but not really, because it drops it for you. It borrows it for you. Okay, summary. The aim of this chapter has been to establish a solid, shared foundation that we can build on in the chapters to come. By now, I hope you feel that you have a firm grasp on Rust's memory and ownership model, and that those errors you may have gotten from the borrow checker seem less mysterious. You might have known bits and pieces of what we covered here already, but hopefully, the chapter has given you a more holistic image of how it all fits together. In the next chapter, we will do something similar for types. We'll go over how types are represented in memory, see how generics and traits produce running code, and take a look at some of the special type and trait constructs Rust offers for more advanced use cases. Nice. So, we're going to cover this in the next stream next week, probably Saturday, but I'll set up the schedule. But this was fun. A lot of reading was fine. Makes me want to go actually type and do some Rust. So I hope you had fun. I hope it was enjoyable. And definitely check this out. It's going to be a great book. It's not out in paper yet, but I'm definitely going to get it when it is. And yeah, so comment, subscribe, all that good stuff. Have a good day. And I'll see you next week. Have a good one.